Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Kristen McQuinn with us today. Hello, Kristen.
Hi, Frank. Thanks for having me.
Well, thank you so much for agreeing to talk about your very awesome article. It's lovely, which we'll get to in a bit. And Kristen, where are you located at?
Today I'm at Rutgers University in New Jersey. I do have a dual appointment. I am also the new mission head of the Roman Space Telescope for the Space Science Telescope Institute.
That is awesome. Congratulations.
Thank you. So I'm spending some of my time in Baltimore at STSCI and some of my time still here at Rutgers. I'll eventually be in Baltimore full time, but for right now, I'm sort of dual citizenship in Baltimore and New Jersey.
Is there like a convenient train or something between them, or do you have to fly? Or
there's a great, you actually can't fly from Newark to Baltimore. There are no major airlines that do that.
I was gonna say.
It's really, so I take the train. It's a really easy trip.
Nice.
But I've got a group of fantastic graduate students here at Rutgers, so I'm still liking to spend some time here, so I get some FaceTime with them.
Lovely. Lovely. And it is February 20th, 2024 as we record this. And how is the winter in that area? Do we have snow in Rutgers?
We do have some snow. We got a bunch of snow this weekend. So, but it's sunny. It's cold out, but it's sunny, and some of the snow is melting. But it is definitely feels like a February day.
Very nice. Very cool. And it is getting a little bit warmer here in Phoenix, even in February. So there's no snow on the ground here. But soon it will become a little unbearable here in a few months. So all good. And Kristen, what do you like to do for research?
My research, I like to study very small galaxies. So some of the lowest mass galaxies, that's right. In the very nearby universe where you can make some very detailed observations and measurements. And I'm interested in how they form, how they evolve in time, the intersection of their dark matter and baryon components, and really just trying to understand the life and times of little things.
Very cool. Very cool. And that is going to bring us to this lovely Little Things article, we'll call it. This one is an APJ. It is open access. It's the open access era, people. Go grab a copy for free. Go get one. The JWST Resolved Stellar Populations Early Release Science Program for Star Formation History of the Local Group Galaxy, WLM. And Kristen, take us away.
Thanks, Frank. I'll get into the science of this for just a bit, but I do want to highlight that this is really an amazing collaboration of people that have put some heart and soul into this paper. Their second author is Max Newman, who is a graduate student that works with me at Rutgers, who has been really, down in the weeds with the data reduction on JWST NearCam imaging. It's a new telescope, new detector, lots of unknowns, and Max has been really getting his hands dirty with the data. Awesome. And Alessandro Savino, I would say the same thing. Alessandro is a postdoc at Berkeley, and this paper would not exist without all of his hard work. Andrew Dolphin has been, a photometry and star formation history guru, and contributed a lot of technical expertise to it. The whole early release science program, the PI is Dan Weiss. Okay. And just not to belabor the point, but Ben Williams also was instrumental in a lot of the data reduction and testing. And I'll mention it as we go along, but this was a lot of work to understand how to use the new detector and use it well. So international team, lots of amazing contributions there. I am the first author on this paper, but it is truly a collaborative effort. And I want to thank everybody that's been involved with this team.
Awesome shout out. Very good. Okay.
So what is this paper about? Well, it's an early release science program. And so for those of you that may not be as familiar with that, before JWST launched, there was a special call for proposals where they selected 13 programs from around the world to sort of test drive, if you will, the instruments and the observing modes on JWST. And each of these 13 programs made up these early release science programs. So they really do, the teams were chosen based on the breadth of working on different instruments and the breadth of science. to really not only help understand and characterize the instruments in this work, but also to help push out some of that knowledge on a short time scale to the community, to sort of help accelerate the learning curve of everyone for JWST. So part of this paper, and it plays into what this paper is about, right? Because our paper has a science focus, the star formation history of the local group Galaxy WLM. But in addition, it's also here to sort of showcase the method with this new telescope and the new data, and to sort of probe and make sure, are we doing it right? Are we getting the answers we expected? Are there any things that need to be, changed in our stellar evolution models to get the right answer in the near infrared? And so there's not just kind of the science theme, but there's also making sure that we are using the telescope to the best of its ability and understand the processes.
Nice, very nice, cool. Okay, onwards.
So the science theme is around star formation histories. And so this means that we are using imaging of resolved stars in this nearby galaxy.
Cool.
And from the imaging of these resolved stars, we're pulling out their magnitude in a number of different wavelengths to create color magnitude diagrams. And color magnitude diagrams really do capture stars of different stages of stellar evolution and different ages, and they inform, if you're, even just looking at a color magnitude in a qualitative sense, you can get a sense for how many stars formed when in the history of a galaxy.
Yes.
And if you can apply stellar evolution libraries in a quantitative way, you can back that out in a more robust fashion. And so this idea of using resolved stars and color magnitude diagrams to infer the star formation history of galaxies goes back, decades now. And HST has really paved the way in order to do this sort of science. And so, the paper starts out talking about the legacy of Hubble on star formation histories. And the literature is rich with all sorts of results based on this technique. The one limitation from Hubble is based on, the quality and robustness of a star formation history depends on the depth of your data.
Yes.
And so, like anything, your results are dependent on the quality of your data. And so Hubble has been incredible in this area and has been groundbreaking, but its limit is its mirror size. And so we can only really get to a certain photometric depth with Hubble based on its sensitivity. And so we've really done a lot of star formation history work in systems within the local group of galaxies, and even a little bit outside of the local group. But with JWST, it offers this big leap forward where we can now go down to very deep depths to do robust and full lifetime star formation histories at farther distances.
Cool.
Okay.
Yeah.
So that's really the setup for the paper, is to really give a nod to Hubble and the landmark results that have come out of Hubble, and then to pivot to what we're getting from JWST in this particular subfield, and what it's going to allow us to do.
Nice. Good. I'm with you.
Okay. So if we go down to the first figure, there's a nice table of data on our target, but we're just going to go down to the first figure because I think that is pictures worth 1,000 words.
Yep, WLM.
There we go. So the idea behind the ERS program in general, I'll just speak a little bit about the broader goals of our ERS program, was to target 3 systems in the local group, a globular cluster, M92, an ultra-faint dwarf galaxy, Draco 2, and this gas-rich star-forming galaxy, WLM.
Yes.
And the reason we chose these 3 targets is because it really does, they highlight, the 3 systems really bracket a range in properties between crowding of stars, and the different, it's populated from stars of different ages. And so each of these targets allows us to probe sort of a different aspect of being able to recover high precision photometry with NIRCam and explore numerous different science goals. So this program, this particular paper, focuses on just this one target, WLM, the star-forming gas-rich galaxy in the local group. And what you're seeing in this image is a ground-based imaging of the full galaxy. overlaid with the footprints from NIRCam, which you see in the center in those solid white lines.
Yes.
We have NIRIS, which is a secondary, another instrument on JWST in that dotted little box down, that's right, which we used in parallel. So we got simultaneous imaging of the main stellar disk of the galaxy, and then one sort of in the outskirts of the stellar disk. We chose WLM as well as the other targets in our ERS program because these are already well studied with Hubble. Right? If one of the purposes is to test drive NIRCam for resolved stellar photometry and to also explore to see whether or not our stellar evolution models are working well in the near infrared for JWST, it helps if you already know the answer.
Yes. Yes.
So we targeted fields that had already been studied with Hubble at optical wavelengths, where we felt we had really good characterization of the data, well understood results. And so we can compare the stuff from this new telescope with, the tried and true older telescope.
Which is not to say there won't be new science results in there.
Exactly, which is not to say there won't be new science results, exactly. But we wanted to start with some of the fundamentals. Yes,
Absolutely.
exactly.
Absolutely.
And so what you'll also see in this image is the dashed, the dashed square. Nope, the one kind of center lower. Right. This is the Hubble ACS field of view that overlaps with NIRCam with very deep data also. So we sort of have a one-to-one comparison on a matched field of view. And then the field off to the right was a WIFC3 UVIS parallel field. And this samples some of the halo of the galaxy, and I'll come back to that really at the end.
Okay.
But the first step in this paper is let's do a deep dive into the data reduction, and let's compare it with what we already know from Hubble.
Awesome.
Okay. So that is giving you a perspective of it. In the next figure, you will actually see the data quality itself. So here are, yes.
Ooh. Wow.
This is the NIRCam field. We're not showcasing the NIRS field in this paper. That will come in a future work. But this NIRCam, these are the two modules. And it's made up of 4 wavelengths of light. So, NIRCam has short wavelength imaging, which is what we primarily use for the science in here. It's the F090W and the F150W filters, and essentially 0.9 microns and 1.5 microns. But you also get long wavelength imaging simultaneously, sort of for free with NIRCam. And so we also have the F250W and the F430W, or 2.5 and 4.3 micron imaging. And so all 4 of those filters were combined to make this 3-color image. I mean, and it's spectacular, right? I mean, the image quality and what you see here is, yes, it's amazing. And just a couple of things to highlight. In the middle of in that middle of the image, you see that bright red star. And if you look carefully, you'll see red sources like that sort of scattered throughout the image.
Yes.
Those are asymptotic giant branch star candidates.
Cool.
We have not simultaneous, but we have additional imaging from Spitzer Space Telescope taken years ago on this, which can help confirm that these are AGB stars. So they just really pop out from the image. They're really quite cool. One of the the AGB stars are they're evolved stars. They're bright in the infrared, and it is no surprise that these really pop out at the longer wavelengths.
Nice.
But one of the things that we were really pleasantly surprised with is that you're not losing a lot in your young star forming regions. And so if you look, Frank, and the left module to the left side, you'll see kind of bluey, purpley regions. Yes, that's exactly.
Like right about here.
It's a younger star cluster. And so you're getting, bluer wavelengths of light emitted from younger stars. And you really are sampling a huge range in the stellar populations in age.
Very nice. Nice resolution too. That is awesome.
Really great resolution. And just one of the fun things that we did with this in the very beginning is, NPR, sorry, not NPR, PBS, the Nova series did a couple specials on JWST, and they wanted to experiment with some of these data. They had me take these images to the planetarium in New Jersey It's the largest dome in the country
Uh-huh.
at the New Jersey Science Center, and they projected it on the dome for us. And we tried to film it. It didn't work out because it turns out that it's dark in a planetarium, kind of hard to film.
Usually. Wow, that's
But it was an unbelievable experience to be able to see these images, the clarity, the resolution projected on a dome.
on big screen. Yeah, right. Yeah, because even these figures don't quite do justice to the resolution.
They don't. I mean, it's a really amazing facility to use. We all feel really privileged to be able to have this kind of data and work with it.
Indeed.
Okay, so if you look closely at these images, I pointed out some highlights, but just to kind of step back for a second, one of the things that grabs your eye immediately are some of the beautiful background galaxies, and even maybe a couple of the foreground stars with the characteristic PSF of JWST. But the real science power in this are all of the little tiny dots of light, right? These are all of the resolved stars in the disk of WLM. And I think about looking up at the night sky. I mean, I know, it's hard. We all get a little bit used to looking at images like this, but this is truly pretty spectacular. And I think about looking up in the night sky and a dark site on Earth where we're really looking up at the Milky Way and the Milky Way stars. And I think that this is what it would look like if we were on a planet in WLM and looking up at the night sky than the galaxy itself. I mean, it's just the stellar field is what we would see. Okay.
Very good. Yes.
So what did we do with the data? Well, from all of the individually resolved stars, you can carefully fit with the PSF photometry each one of those sources and pull out a carefully measured flux and uncertainty of all the resolved stars. And this was part of our ERS mandate. Part of it was to be able to develop the photometry tools and the methodology for being able to do that in a really precise way.
Cool.
So we did that. And this was all lots of sweat equity went into that. I think we did about 600 different photometry runs testing how to best work with the data and recover the highest fidelity photometry. And the result of that work is shown in figure 3, just below.
Before we get there, I want to point out that this testing run also benefits other pieces of sciences because they will pick up your PSFs and go. Yeah.
Yes, in fact, the PSFs that we used are coming out of the web PSF model. It's a tool that's was made by the Space Telescope Science Institute. But we did initially find that the PSFs that were created weren't quite accurate enough. They were had too much flux that was in the central pixels of the PSF, and so it wasn't. It was still pretty precise, but was leaving with error bars of a few percent. And Space Telescope has now updated the PSF model, including more of the technical performance of the detector. And now the PSFs are actually a much better, closer match to the real observed PSF. And so our photometry has improved even more. And that was, a really key part of the ERS program. And the outcome is quite encouraging. I think that we are going to be able to do some amazing science with NIRCam.
And here we have 600,000 stars resolved. That's amazing.
So this is the color magnitude diagram that we produced from the short wavelength modules, detectors on NIRCam. And we're recovering about 600,000 high fidelity sources. And you can see that they're, in this color magnitude diagram is populated in nearly all parts of the stages, on all stages of stellar evolution. You have where your cursor is right now, you have the main sequence of stars. And over to the right, you have the red giant branch. There's also AGB stars present, helium burning stars, the horizontal branch, the red clump, which is amazing. But and you can see how good the photometry is based on the tightness of these sequences, right? The red giant branch is super tight, and so is the main sequence, which is just a testament to the how good the data are and how good our tools are working and how good the PSF model is.
And what are our uncertainty things here on the right? This is the photometry.
Yes, that is photometry based on not only Poisson statistics, but also based on artificial star tests that were done.
Okay.
So it includes artificial star test uncertainties.
And this dash line, this cut, what is that?
That marks the 50th percent completeness limit. So
good. Okay.
and so focusing on that line, you know, right above that line, we are reaching the feature in the color magnitude diagram that corresponds to the oldest main sequence turnoff. And so these are where, yeah, these, you know, stars are just starting to peel off of the main sequence. And it is this feature that happens obviously at very faint magnitudes that is a key part of being able to accurately and robustly fit for a lifetime star formation history.
Yes.
So it's kind of a key point to this. And this is overall, if I just step back for a second, it's one of the you know, deepest CMDs of a nearby galaxy that's ever been done.
Cool.
It is you know, the really close ones obviously have gone deeper than this, but at this, you know, outskirts of the local group, this is exceptionally deep.
Nice.
It's actually deeper than we were expecting. The exposure time calculator was conservative, and we ended up getting deeper than we anticipated. We've actually done a deep dive on this, and as a new upcoming paper by Alessandro Savino, one of the authors on this paper, doing a very careful comparison of actual data with the estimations from the exposure time catalog, the exposure time calculator. And we're finding that with some tweaks to the ETC, it could actually produce more realistic exposure times needed, and in some cases save up to a factor of 5 in exposure times in the telescope.
Okay.
Which is kind of a big deal because this telescope is highly oversubscribed. And so if we can optimize and reduce the time that you actually need to achieve your science goals, this is a big win for the community.
Can access, right?
Yeah.
More science per time.
More science, right. And less time per program.
Oh, per science, there you go.
So anyway, so it's a really, I want to just speak just a minute on the depth of the CMD and why it's so important.
Yes.
So when you fit, you know, I can look at this and say, okay, there are some young main sequence stars in this color magnitude diagram. I know that the galaxy has formed stars at a recent time. I can see an RGB. I know that there are some, you know, older stars that are formed in the galaxy. But if I can fit this with stellar evolution models, you know, we can quantify that as stars formed per year.
Yes.
However, there is an age metallicity degeneracy in things like the red giant branch.
Yeah.
And so it's somewhat hard to, you know, age date an RGB star. Is it 10 billion years old? Is it 7 billion years old? Especially with the, you know, with the metallicity degeneracy in there. But if you get down below the oldest main sequence turnoff in your CMD, you can break that age metallicity degeneracy. And it's really because the oldest main sequence turnoff, the morphology of that feature in a CMD space uniquely depends on age and metallicity. And so if you can get down to that depth, then you can accurately reconstruct the ages of the stars early on in the universe.
Nice. Very cool. Cool. And what is the rough metallicity with WLM?
It's about 15% solar. There's some debate in the literature whether it's about 10% to 15%. So it's low metallicity.
Okay. Okay.
Okay. So we'll go down to the next figure, if you will, Frank.
Okay, figure 2, CMD. Let's go down to figure 4.
Right. And so if you recall in that earlier figure where we had NIRCam and ACS overlapping in that field, what we've done here is the test. So we've taken stars in the matched aperture between the two telescopes, and we're plotting the CMDs from those two fields. And so you'll notice there's only 200 stars now from NIRCam because it really is just a smaller section of the NIRCam footprint. And here's the stars recovered from Hubble in ACS in the exact same footprint.
Okay.
The Hubble data are very deep, but the NIRCam data are deeper.
Yeah.
And so you notice that in the star counts, there's 60-odd thousand in ACS versus 200,000 in NIRCam.
Right.
If you go above the upper part of the CMDs, the star counts are pretty well matched, but the highest, the extra stars come from the bottom of the CMD and NearCam,
Yeah.
because we are going a fair amount deeper, and because of the IMF, you know, you got a lot more star
Yes.
counts at lower masses and at faint magnitudes, and so that really beefs up the number recovered in the NearCam filters.
Nice. Okay.
And there's some differences, you know, the ACS has a optical band, optical color baseline, and you get a little bit of a wider CMD. But the features, you see the similar features, right? Main sequence,
Yes.
red giant branch, red clump, all
Yep.
things.
Cool.
It's a nice comparison.
Yeah, very good.
Okay, so now what did we do with the data? We've got these beautiful CMDs. And so if you go down, we're going to skip the next figure. It's not as critical, but we'll go down to
Matches.
here we go. So when we, to derive the star formation histories, we take the data, the CMD, and we try to generate a synthetic CMD from the stellar models and match the observed CMD as well as we possibly can.
Okay.
And we do this with different stellar libraries, and we've done it for both NearCam and ACS, right? So we're still test driving everything to make sure we get the right answer.
ACS bottom, NearCam on top. Okay.
And the left columns are with the Parsec library, and the right panels are with the BOST stellar library.
Okay.
Just for simplicity, let's zoom in on the upper left.
Oops. Okay, upper left. Parsec, NearCam.
Great. So what you're seeing in the top left is just the observed CMD. This is just the data plotted as a 2D histogram. On the right, this is a synthetic CMD generated using the Parsec stellar libraries. And we you know, the code iterates on it until we get what we think is the best match to the data. So these two things should look the same. The right and the left should be a good match. The bottom left is just a straight residual where we're subtracting the modeled 2D histogram from the observed 2D histogram. And on the right, it's got a weighted significance. And this is really kind of the money plot when you're looking for how good a fit is. You ideally want no structure in this residual. So and mostly you see you know, a lot of just faint coloration with not a lot, but there are a couple areas that stand out, and that's where it tells you that the models aren't quite matching what nature is doing.
Right. Okay.
So in particular, one of the things that you'll see is one of the things you highlighted right there in the center is the red clump. The red clump, it's notoriously difficult to match. And one of the things that makes it stand out in particular is that it's a high density region in the CMD. And so the difference, the residual significance also stands out because it's got a lot of higher density of sources in that particular CMD part of the space. But we know the red clump is difficult to fit. It's hard to fit in the optical. So this was not a big surprise or really of significant concern for our purposes.
Binaries. Do you filter binaries, or are there hidden binaries in here?
We include a binary in the assumptions in our fits. So we use a flat mass ratio distribution, assuming about 35% of binaries. So that's included in the fit. We also assume an initial mass function. This is done with the Krupa IMF. We also impose some constraints on how the metallicity increases with time. So we, you know, assume that it's more metal poor at the beginning of the universe and more metal rich today. Pretty simple constraint. We also assume a distance to the galaxy. We use a well-measured tip of the red giant branch distance to WLM. And we include some model of the foreground extinction, which is pretty minimal because this galaxy is at a high latitude.
Yeah, it's way on the outskirts there. Okay. Cool.
Yeah, I will note that there's a little bit of coloration around the red giant branch where the blue is basically showing where the model over predicts, and the red shows where the model under predicts. And you can see there's a little bit of an offset for the red giant branch where the Parsec models are wanting them to be just a little bit redder than they are. We see that a little bit in the optical too, but overall, I think this is a really good fit. residual significance range is set by the mismatch in the red clump, and the rest of the CMD is really within a few sigma.
Yeah, okay. Very good. Okay.
So having produced a synthetic CMD that we think is a reasonably good match to the observed CMD, we then take the star formation history that went into creating the synthetic CMD and we plot it.
Okay.
So I think that should be in our next figure, if I'm not mistaken.
Do you believe that is true? Best fits tenure cam, star formation history of WLM, and here we go.
Perfect.
Let's get both up and we'll zoom in as need be.
Okay, so let's start on the left. So what we see there on the left is that best fitting star formation history that created that synthetic CMD. You have the fraction of stellar mass formed as a function of look back time. The parsec and the Basti fits are both shown, right? One in just a solid and dashed line. They are in really close agreement with each other.
Yeah.
The faint shading along those lines are the statistical uncertainties. We do not have the ability yet in the code to do systematic uncertainties, but the range in the solutions between the two libraries gives some indication of what the systematic uncertainties will be.
Yeah, very nice. Okay.
The dashed line across is just a constant star formation rate. And then on the left in the shaded region, vertical line is corresponding to about the epoch of reionization at early times.
So very metal poor over here, metal rich over here. Yep.
Well, that's the star formation history. That just is showing how much mass is being formed across time. In the lower plot, we're seeing the metallicity evolution. And so there you're seeing metal poor at the early times and metal rich at the present day.
Okay.
Okay.
Cool. Okay.
So one of the unique things that we did in this paper was to also check our metallicity fits. And these are a little bit harder to check historically because you need a lot of spectroscopic observations of stars in the galaxy to really do a comparison of the metallicity evolution from CMD fitting. But WLM is very well studied, and there's some fantastic work in the literature by Lehman. He's got there are a couple of series of papers where they did spectroscopic analysis of 100 or so stars in WLM.
Okay.
And so that's what we're showing in the right plots here, is that we took in roughly the same field of view, the same part of the galaxy in WLM, and they did a metallicity distribution function of those stars. And we generated a metallicity distribution function from our best fits and overplotted them with the parsec from the Basti models. And so what you're seeing in the top plot, and then in a cumulative way in the bottom plot, is that our age metallicity relations and our metallicity distribution functions are actually a really good match to the spectroscopically determined ones.
Yes.
This gives us additional confidence that our fits are good.
Good. Okay. Yeah.
Okay, and so in the next plot, we move on to what I believe will be in figure 9, a comparison of our fits with fits done from the Hubble data. And so let's just focus on the top plot for a moment here.
Okay.
This one, we show the same fits I showed before from near cam in using parsec and Basti. Those are the red lines, but that is just now in the field of view that overlaps with Hubble.
Yes.
In blue, I've got the star formation history fits from the Hubble data, again, in only the overlapping fields of view. So it's kind of a one-to-one comparison.
Yes.
And so just looking at the red and the blue lines, this is beautiful agreement of all ages. I mean, they really do, regardless of the model and whether it's JWST or Hubble, the fits are in excellent agreement. And that gives us a lot of confidence in our star formation history tools.
Awesome. Right. The whole work.
One of the other things we did, which is really, it's going to be hard, never been done and hard to do in the future, is that we did simultaneous photometry on the Hubble and JWST data.
Oh, nice.
So we created a catalog of all 4 wave bands, and then we simultaneously fit all 4 for a star formation history.
Okay.
And that's shown in green.
Yes, nice.
And the green lines, again, overlap with everything else, which tells us that, you know, when we did the combined ones, it was from the optical and the near infrared. You got more information. You're sampling a greater amount of a spectral energy distribution of all the stars.
Yes.
And we get the same answer when we do just optical or just near infrared. And so it tells us that, you know, with less data, with just 2 bands, we're not missing anything.
Yeah.
Also really important. And I say it's probably not going to be done very much in the future because
Yeah.
we've already got really, really deep data on Hubble. You know, I think it's going to be hard to go back and say, oh, I need really deep data on JWST too, because you've already kind of done the science. So practically speaking, it probably won't be done very much.
Okay.
Okay. And so this plot is really demonstrating that we have met one of our goals in the AAS program of testing the photometry, you know, seeing if we're doing things right, and charting a path forward for star formation histories with JWST. Right, we are now showcasing that we know that we can do this as a community. We have the tools; it works super well, and so let's go.
Let's go. Let's go. Although this one's pretty good all by itself. Let's go.
Right. Well, and I want to pause here though, because there is science that we are getting from, you know, it's not just a check, but it's also some really, you know, interesting conclusions from the star formation history. So I'll back up a little bit and talk a little bit about WLM as a low mass galaxy, right? We know these things, we think these things formed early in the universe. Very, very low mass galaxies are thought to be zapped by the epoch of reionization, where you have this, you know, copious amount of UV photons being produced by stars and galaxies, and it heats the gas in very small halos, and in combination with stellar feedback, it, you know, it sort of shuts down star formation.
Right.
When you get to the mass regime of WLM, this is above that mass regime. We do not expect something like WLM to be quenched by reionization, but that doesn't mean that it can't be affected by it. And I think that's what we're seeing in this star formation history. So if you look at the very oldest look back times, the galaxy formed, you know, roughly 15% of its stars in the first gigayear or so, that early epoch of star formation. Of the universe, and then it kind of got quiet, you know, for about 3 or 4 gigayears. It just it sort of plateaued, you know. It's sort of this post reionization pause, and it's difficult to say for sure whether it's because of reionization, although, you know, it is one of the more likely reasons or explanations for that's causing this pause. There could be other reasons, but we do see this sort of period of quiescence.
Yes.
Or star formation after a few billion years is reignited, and the galaxy continues to form stars at roughly a constant rate today.
Yes. Okay.
And so, you know, this is interesting because we don't have very many gas-rich, relatively isolated galaxies like this with the data deep enough to study it at the early ages.
Yes.
And so it's really, you know, there's only 2 other galaxies, Leo A and Aquarius, that really fall into this mass regime, that are isolated and have star formation histories done from the requisitely deep data, and they show very similar patterns.
Okay, interesting. Same plateau, quiescence? Same
plateau, early start, and then it kind of gets quiet. So it's a little early to say whether this is sort of a pattern, you know, with only 3 galaxies, but it is intriguing, and they are, you know, the sample that we have so far. You know, if you get to be a little bit more massive than WLM, you know, we would expect a more constant star formation rate at all times, and that is in fact what we see in things like the SMC or the LMC.
Yes. Okay. Very interesting. Okay.
And so that's the crux of that's the crux of this paper, is just showcasing the beautiful data from NIRCam that we've got the tools to do star formation histories and do them very well, and that we're getting some insights on the star formation history of low mass galaxies that are really interesting. And I think there's a lot of connection here between what we're seeing from galaxies like this and the high redshift universe, right? Where the high redshift community is really trying to focus on what this first epoch of star formation looks like in situ. And
Mhm.
we're trying to study what that epoch of star formation looks like from a stellar archaeological perspective, right? Of
Right.
pulling it TMD. So there's a lot of synergy there. And I think that we're still waiting for some of the really deep data to come from the high redshift community that will image and sample galaxies in this mass regime. They haven't quite hit this mass regime yet, but I'm really looking forward to comparing results to those when they come out, hopefully next year.
Very nice. Very nice. I call good science. It connects to other pieces of science. It's very nice. Very lovely, lovely, lovely. Kristen, I want to thank you so much for walking us through your very awesome article. Very nice.
Very fun.
And you kind of touched on it a little bit there as you went through. And so let me just ask, where do you think we go from here, given the published article? Will there be another JWST campaign on this object? Are there other objects, not high redshift, that one could go after? And just sort of next steps, maybe Roman can pull something out. So where do you think we go from here?
Well, we do, you know, if you think back to that first image where we have lots of footprints on WLM, there's more data from JW that we have yet to analyze. And there is Roger Cohen, who's been a postdoc working on the data, is actually going to take all of the data from NEAREST, WFC3, UVIS, ACS, JW, all of it, and do a spatial analysis of maybe looking for a radial age gradient in WLM. So that's upcoming. But to follow up on the main science theme in this program, I have a medium-sized cycle 1 program on JWST that has very deep data on a very low mass galaxy called Leo P. Leo P is about 2 orders of magnitude smaller than WLM, less massive, and it is outside the local group and very isolated. So we are been working hard on that data. They're exquisite, and I hope to have another paper out on the star formation history of another gas-rich, isolated, low-mass galaxy within the next few months.
Very nice. And I look forward to seeing that one. I'm curious if there's still a plateau. So we'll find out. We will find out. I won't ask. Very cool. Kristen, I want to thank you so much for walking us through your very lovely article. It's been great.
Thank you so much, Frank. It's a pleasure to be here.
And that will do, everyone. And I hope this makes your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.
Bye-bye.